Welcome to the Climate Hour. I'm your host, Bob Grove. Today, we're going to talk about some really hard climate science, volcanoes and rocks. It doesn't get any harder than that. And by hard, I'm not talking about being difficult to understand. I'm talking about formal scientific methods characterized by controlled experiments, quantifiable data, cumulativeness, replicability, and the high degree of accuracy, objectivity, and consensus that leads to testable client science predictions that stand against any rational evaluation. Hard sciences like geology. Geology is the study of our planet's solid materials, its rocks, the minerals and the processes that shape and form them. Or geomorphology, which is the study of our planet's surface, its mountains, its valleys, rivers, and coastlines. Geomorphology seeks to understand why landscapes look the way they do, how they evolved, and how to predict how they're going to change in the future. Landscapes are changed by things like water, wind, ice, wildfires, chemical reactions that form and break down soils, and interactions with life on the surface, including humans, all mediated by climate. In other words, our planet's surface and its landscapes are an intersection of climatic, hydrologic, and biologic actions upon the underlying geology. Geomorphology helps us understand how climate is going to affect the landscape and the things living on it. Volcanology goes even deeper below the planet's surface to study lava and magma. We tend to think of major volcanic activity as associated with prehistoric eras like the Jurassic period. We've all seen the movies, the dinosaurs grazing before a backdrop of erupting volcanoes. The thing is that increased volcanic activity is often associated with the warmer interglacial periods throughout our planet's history. Increased volcanic activity may actually be our planet's way of slowing down a runaway period of global warming. So our planet can cool itself, but what does that mean for the life forms living through the increased volcanic activity in the subsequent ice age? These hard sciences, the rocks, the volcanoes, they help scientists chart our planet's historic cycle of warming and cooling. But perhaps more important, they give us a baseline for comparison to today's accelerated period of man-made or anthropomorphic global warming. And current rates of volcanic and geomorphic change may help our scientists predict and prepare us for the climate change that's coming down the road. We're joined today on Zoom by Paul Bierman. Paul is a geoscientist and author. He is a professor of environmental science at the University of Vermont, where his research and teaching focus on the interaction of people and Earth's dynamic surface. Paul's wide-ranging interests include climate, geochemistry, erosion, science communication, and broadening participation in science. Hi, Paul.
Hi, Bob. Thanks for having me.
Richard Hazlitt is a geologist and author. He's a professor emeritus of geology and environmental analysis at Pomona College in California, an affiliate faculty member with the geology department at the University of Hawaii, and a research associate with the U.S. Geological Survey's Hawaiian Volcano Observatory, where he's currently studying the eruptions and history of Kilauea volcano. Rick is the lead editor of the Oxford Encyclopedia of Agriculture and the Environment. Hi, Rick.
Good morning.
I'm always curious about the pathway that leads us to become scientists and authors. So before we get started, I'd like to maybe learn a little bit more about your path. Paul, what was the path that led you to becoming a geologist?
Oh my, I think that was a convoluted path. My mom would say I knew I was going to be a geologist when I was about 4 years old. There's a great photograph of me that doesn't work well for a podcast on Cape Cod with a bucket full of rocks, and I collected those rocks. And when my folks moved out of their house, I got all those rocks back that I'd collected. But really, what got me, I went to college thinking I was going to be a chemist, and I needed one more class, and I took a lakes and oceans class that just happened to fit in the right slot in my schedule. And after, I don't know, a couple months of fall semester being in honors chem lab in the basement twice a week and being outdoors in this lakes and oceans class, I realized that I love doing chemistry, but I really preferred doing chemistry on things related to the earth and became a geology major. And I haven't really looked back much since then. I love being outdoors. I love understanding how nature works. And I really enjoy trying to understand the interactions between people and the environment. And that's driven my career for 40 some years.
Rick, what about you? What led you to the hard science? Specifically, what led you to volcanism?
Well, I grew up in a military family, and as a lad, we moved across the country frequently from one post to another. And my father, I think very wisely, took the time to extend those transfers into vacations so that we visited various national parks and monuments. Uh, and for me, engendered a sense of real interest in history and context. In other words, uh, how do I fit uh, coming into this consciousness or reality in the context of history and space and time? And so I read a lot about nature and the out of doors, and I was interested, like Paul, at a very young age in getting out and exploring the environment. One of our military visits took us to Hawaii, and there at the age of 10, I became acquainted with Kilauea, which is the world's largest active volcano, and actually uh, one of the most accessible, not the largest active volcano, but the most active volcano in the world. Very accessible, and I thought, wow, this is really not what I thought a volcano should look like. There's something really different about this landscape. How the heck did it become this way? And I've spent the rest of my life more or less answering that and a few other questions about the great out of doors. So, like Paul, I was drawn to the wider world and simply wanted to know what it all means and enjoy the process of figuring it all out.
You mentioned accessibility. Ironically, Kilauea Volcano is a national park. People come just to stand there and look at the crater and the lava.
Oh, it's impressive during an eruption, particularly at night when it's so beautiful to stand close to the rim and be surrounded by uh, other people from Spain, Germany, the Far East, all parts of the country. It's an international showcase, really a wonderful place.
So let's get into the science a little bit. Paul, talking about the history of climate change, I mean, how does science inform us of that? How do we know what the history of climate change is? I mean, what does the geology and geomorphology tell us about that climate change history?
Well, we know that Earth's climate has been changing continually and forever. We can look back on the rock record and we can go back millions, even billions of years and see evidence for prior glaciation of our planet, the deposits left by glaciers that are long vanished at this point. We have a number of other ways using chemistry and using isotopes, different forms of particular elements that tell us that the climate has changed over time. And we can do that on all kinds of scales, again, from the billions to the millions to the hundreds of thousands and the tens of thousands of years. We do know that right now we're living in what we call an interglacial, a warm period between glaciations. And if we go back sort of the last 2.5 million years or so, the Earth has swung between these relatively warm periods like we're in today and much colder periods when ice covered much of our planet. Ice sheets covered where I live here in Vermont, about 2 miles deep over my house. Ice did not cover where you are in Hawaii, although certainly in the high peaks there was ice. Um, and so Earth's climate is constantly changing, but that's not to say that the change we're seeing now is anything natural. It is happening at a rate far faster than nature has almost ever changed this planet. So we have a whole bunch of tools. We have well over 150 years of scientific evidence that shows that the climate on Earth has changed over time. And I think the big difference in the science over the last half a century or so is we have refined our understanding of the physical reasons, the forcings that climate changes, the time scale over which it changes. So we actually now have a really good idea of what the climate has done over, I would say, the last couple million years, and even a better idea of what it's done over the last few tens of thousands of years. And we can go into as much depth as you'd like on how we know that and where we know it.
Well, that's great. Rick, what about volcanoes? I have this impression that they're Earth's way of slowing. or, maybe bringing to an end these interglacial warming periods. How does that work? Is that true? And how does that work?
There's an interaction between volcanism and climate that goes two ways. So volcanoes can certainly influence the climate and vice versa. In the case of the interglacials, when as the Earth orbits the sun, it goes through changes in distance and tilting in its plane of orbit. And these are the primary factors involved in forcing a cyclical climate change between ice ages and interglacials. So volcanism plays a secondary, but not necessarily trivial role in terms of developing this cycle. We are in an interglacial right now, as Paul mentioned, which began fairly abruptly, starting about 20,000 years ago. And at that time, about a third of the Earth's surface was covered with thick ice caps. That compares to about 11% now of the land surface of the Earth, about 30% land surface 20,000 years ago. Over a period of 10,000 years or so, this retreats. And ice is a very heavy load on the Earth's crust. And there are a lot of areas where glacial ice covered volcanoes, as it does in Antarctica today. There are almost 200 volcanoes covered by the West Antarctic ice sheet. So you take that ice off rather abruptly, and that reduced pressure on Earth's mantle, which is the source of the magmas that feed volcanoes, actually triggers melting and makes it easier for volcanism to take place. So we find at the end of the Ice Age, removal of the ice sheets, say in a place like Iceland, for instance, which was largely covered by ice, stimulated the onset of volcanic activity, maybe 100-fold there. A great increase in volcanism as the climate warms up. The abrupt increase in temperature that took place at the end of the Ice Age, quite abrupt compared to the gradual decline in temperature at the start of an Ice Age. Yes, volcanoes may have played a factor in that too, because volcanoes put out a lot of carbon dioxide, and that warms the atmosphere. It acts as a positive feedback on top of this orbital forcing, and that could really accelerate the warming climate to conditions we see today.
So I'll just chip in there that I think what's really important to understand is this idea of feedbacks, that the Earth system for a little bit of push doesn't always respond in the same way. And the feedbacks are actually something about the climate system that we've learned a whole lot about in the last couple decades. But for example, as you start to melt an ice sheet, that is, you can think about as a great white reflector sending sunlight back to space. As you melt that ice sheet, you expose ground underneath, and vegetation comes on, and those are way better at soaking up that incoming solar energy. And they further warm the planet, which further shrinks the ice sheet. So these kinds of feedbacks are really important. And they take that orbital forcing, which is very subtle, that Rick talked about, and they magnify it. And they can also lead to things that we call tipping points, where things are going along smoothly, and then these forcings can amplify what's happening to a point where there are major and dramatic changes.
And you both mentioned this orbital variation. I think that's referred to as the Milankovitch cycles. And
That's right.
roughly 100,000 years for this orbital variation, maybe, or take. So the planet receding or getting closer, the tilt, whatever, heating and cooling cycles. And if I understand correctly, the glaciation periods are larger, 80,000 years for ice, and then these shorter warming periods, 20, 30,000 years. Is that close?
Well, sort of. There are actually three different orbital parameters. One operates in the 20 to 25,000 years, the other in the sort of 40 to 45,000 years, and the last one, it's sort of the 100,000 year cycle.
Okay.
And they don't actually change the amount of solar radiation coming to the Earth. They change where it comes to Earth. And the magic point seems to be high latitudes in the northern hemisphere. So think Canada, 60 degrees north. And if the summers are cold enough or cool enough in northern Canada, then the snow that fell the winter before it can't melt. And so if you look at the orbital forcings, it's when that 65-degree north amount of energy decreases, and there might be more energy in the tropics, but that doesn't matter for glaciers. And that seems to set the pacing of glaciations. What's interesting is none of those three cycles line up well with when the glaciers expanded and retreated. But if you look at the time, if you look at the as I say, the pacing, the reproduction of that, you'll find these 20,000-year cycles, 40,000-year cycles, and 100,000-year cycles mixed into all kinds of things on Earth. So the cyclicity is determined by the orbits, but it's those feedbacks on Earth that add that all together to give us a pacing of glaciation that over the last million years is about every 100,000 years. We'll have another glaciation, and then it'll warm up. And as Rick said, the warm up is fast, and that is almost certainly from feedbacks. Possible volcanoes are part of those, but this ice, what we call the ice albedo feedback, what I talked about, when the ice sheet starts to melt, the reflectivity of the Earth goes down. That's a really positive feedback. The ocean's involved, carbon dioxide's involved. All of these things are involved. But I think the important thing is you talked about going between scales on climate change. Everything that nature does is happening on a far longer time scale than what people are doing. And that's typically a confusion that those of us who work in climate, and especially when I teach climate, have to help the students sort out. That the human time scale is uniquely rapid. And a human time scale is land clearance and fossil fuel combustion. And it's really disconnected from the geologic time scale completely. And again, that's something that can be very hard to communicate and to realize that both things can be true, that nature changes climate all the time and humans are changing climate, but they're on just totally different timescales.
And we see this argument. The climate deniers say this is normal. The Earth's gone from warming periods, cooling periods throughout eons. So why is today different? But if I understand the Milankovitch cycle correctly, we should be moving into an ice age right now. Why is it so hot out there if we're supposed to be getting an ice age?
Well, um, there are several people who have actually postulated that you're totally right. We should have been sliding into an ice age at least 5,000 or 6,000 years ago. But guess what else was happening 5,000 or 6,000 years ago? The beginning of domestication of animals and farming and rice farming. And it's still rather controversial, but there are folks who think that humans have actually been affecting climate for the last 5,000 to 8,000 years by what we've done, and we have reversed that trend. I find the data somewhat equivocal about that. There are interglacials that have lasted upwards of 20,000 years. In fact, one that I've spent most of my time studying 400,000 years ago lasted 30,000 years. So it's hard to know whether we should be sliding into cooler times now, but it is not hard to know that the climate is warming dramatically at this point, and that is absolutely and unequivocally human driven.
Yeah, Rix, what's your thoughts? I mean, is this just another interglacial period, or is there something different about today's global warming?
Well, I take a perspective that if you look back at the last 2.5 million years or so, 90% of the time, maybe a bit more, the Earth has been characterized by much colder and less stable climate than what we're experiencing at present. In fact, it can be argued that so unstable have conditions been that the only way that the human race could adapt and function in this environment was by hunting and gathering. So the blessing of an interglacial for us is that it has enabled conditions for civilization to develop. To the degree you believe that's a blessing, here we are. And most of these interglacials have been fairly brief. 20, 30,000 years is an exception. They've lasted only a few thousand years effectively before conditions really begin to cool and we slide on back down again. So I think that we really are dealing with a superposition of human activity on natural conditions that have extended or stretched the current ice age. I'd taken a look at a lot of the data regarding methane production from the development of rice, for instance. And if you look at the methane cycles, uh, the data preserved as gas bubbles trapped in ice, something that Paul knows a lot more about than I do. You find some exceptional rates of increase at a time when methane should be decreasing, beginning with the development of agriculture. So I think that we are in the driver's seat as far as determining how this interglacial will end. That what's at stake is not human life, and people will persist. We're an amazing species as far as that goes, but certainly will civilization keep going? And will we be able to impart our legacy in terms of what we've learned and perspectives we developed indefinitely? That's the sort of stewardship that I find in jeopardy in considering the environmental change that we must address one way or another.
That's
Guess
interesting. Go ahead, Paul.
Oh, I would say I'm a little less positive, although I tend to be a positive person than Rick. I think if we don't address climate change induced by humans, and I'll preface this with I think we absolutely can address it. It's a choice of whether we do or not. If we choose not to, I think we're headed into territory completely uncharted for humankind. And partially because there are 8 billion people on this planet right now, and we need the ability to feed them and to have clean water and to have safe places to live. And as the climate system heats up and becomes more volatile, as I think we've all seen in the last decade or two with extreme events, we're going to see things like sea level rise. We're going to see large parts of the planet be too hot to live in without air conditioning, like I see over Rick's shoulder there, or the heat pumps that you can't see in our house because they're around the other side. There are literally maps showing by 2100 large portions of the planet that will no longer be habitable by people without conditioned air. And so I think we're setting ourselves up with this huge population boom of the last 100 years and destabilizing our climate for sort of dramatic catastrophe and a shrinking of the size of the human population, and I think a degree of misery we've probably never seen before as food supplies shrink and water supplies shrink. And every prediction I've seen shows that by 2100, we are going to be able to grow less food and we're going to have a lot less in the way of water supply. So again, I don't want to come off as a doomsayer. I'm not, and I don't think being a doomsayer on climate has done the sort of, how do I say this, climate positive movement any good. Because I think what we need to do is present solutions, not just scream about problems. And I really hope, and I see just in things like the adoption of solar power and the price crash of solar power. If you look at the price over the last 20 years of what it costs to generate a kilowatt hour of solar, it's cheaper than building a natural gas plant. It's cheaper than building a coal plant right now. So, when you see things like that, it gives me hope. But what I haven't seen yet is the global action to tackle this change in climate.
Yeah, it's interesting. You're drawing a distinction between individual humans and civilization, and I think to address what you're saying, Paul, it's we've got more people on the planet than ever before, and really, as a civilization, we're more exposed just because there are billions of people, and how do we feed them, and how do we, temperature control, cooling, warming. We've whatever the cycles have been, we've never faced the challenge of this many people trying to survive. To speak to what Rick is saying, climate may, we may lose part of that population. We may lose civilization. I'm hearing you say the ice age has come along and we have to revert back to hunting gathering, smaller pockets of humanity surviving, but in a much more rugged, primitive environment. So it'll be interesting to see where we go. Kind of brings us to where we are now. Where is, what's happening with climate? How's that affecting morphology and all these other issues we're addressing today? You're listening to the Climate Hour. I'm your host, Bob Grove. We're speaking with Richard Hazlitt and Paul Bierman about volcanoes and rocks. So let's talk about the current climate impacts on, say, geomorphology. I mean, what are you seeing, Paul?
Oh, I'll reflect back on my my local geomorphology, Vermont has seen 200-year storms each of the past summers, so one each summer of the last 2 summers. And those have reshaped our river channels. They have destroyed bridges. They have taken out roadways. We are seeing rainfall intensities beyond what we've seen typically in the past. We're seeing storms lasting for longer. That's not only triggered flooding, but it's also triggered landslides. 2 summers ago, we had massive landsliding across the state from saturation of ground that we typically don't see here. So we're seeing direct climate impacts here. We're seeing them on our winter sports industry. We just had what most people here would call a good old-fashioned winter in Vermont. We finally had snow on the ground that lasted 8 or 10 weeks. The last 10 years have just not been like that. But then again, 2 weeks ago, it warmed up and it was 60 degrees, and that snowpack literally vanished in 2 days. And that, that seems to be the new norm now. So we're seeing changes in how the landscape's responding, but we're also seeing changes in sort of this ephemeral landscape that we have in the winter with snow, which is, of course, economically hugely important for our state in terms of skiing, winter sports, and that sort of thing. Maple syrup, that when we first came here 30 some years ago, you would not see anybody boiling maple sap until usually early March. And now there are people who are out tapping trees some winters in January because it warms up enough that they can get enough sap to boil. So it's landscape changes that then are intimately tied to the cultural norms of a place that are changing. And so the maps, the predictions I've seen from the Vermont climate assessments by 2100 put us somewhere in the Western North Carolina, Tennessee area for climate. So, ask any old time Vermonter whether they want to be living in Tennessee or North Carolina's mountains, and they will almost assuredly tell you no. But that's where our climate is going to evolve to if we keep on this path. And so I find when talking to people that that's much more tractable than saying, oh, we're blowing through the 1.5 degrees Celsius Paris Agreement. But more, can you imagine, a place hotter than where you live today with a different culture and that becoming your culture? I think that's very tangible to folks. The other geomorphology piece that I think we all need to be aware of, and I actually think is I don't know, it's the climate elephant in the room, is sea level. And we don't pay enough attention to the fact that if we lose the world's ice sheets or part of the world's ice sheets, there are going to be tens to even a few hundred feet of sea level rise around the world. Now, the few hundred feet is long in the future, and we would have to melt away all the ice. But the predictions for 2100, when I can confidently say I will not be around anymore, but maybe my kids will be around and quite elderly, predictions for then are at least a foot and maybe as much as 5 feet of sea level rise. So when I'm teaching my intro climate class, I say to every student, I say, close your eyes. I'm going to close my eyes now. And imagine your favorite beach. Now imagine that favorite beach with 5 feet of water on it, 10 feet of water, 20 feet of water, because if we lose the Greenland ice sheet, that beach is going to have 20 feet of water under it. And for you all in Hawaii, that's probably pretty easy to think about, right? For those of us inland in Vermont, it can be a little more difficult. But that's the kind of personal effect that climate change is going to have. Yet that sea level rise, if we say melt the entire Greenland ice sheet, is going to displace 500 million people. Think about that number. 500 million people are not going to have a place to live, a place to work, or a place to farm. That's, we fuss over migration now around the world. Think about 500 million people moving and what that's going to do to global stability. So there's a lot of geomorphology change that happens when we change climate.
Absolutely. A huge bulk of our population live in coastal regions, so they are going to be affected. Rick, what are you seeing? I mean, how is current global warming affecting volcanology or anything else you're dealing with?
Yeah, to follow up a little bit on what Paul said, of course, you see some changes here in Hawaii too that relate to a warming climate, but we're buffered in the East Mid-Pacific by thousands of miles of ocean, so perhaps not as pronounced a change. The oceans are becoming more acidified, so coral bleaching has become a big issue for some of the reefs around Hawaii, and the climate has dried out some here as well, which leads to a more concern about fire seasons and the like. As far as the volcanoes go, the amount of change that has occurred is so far not a factor that has any impact in terms of the increase in volcanism I mentioned took place with the end of the last ice age, 20 to 10,000 years ago. But it might in places like West Antarctica. That ice sheet, were it to melt, would raise the West Antarctic ice sheet sea level by what, 10 to 15 feet or so, comparable to Greenland. It overlies a lot of volcanoes there, as I mentioned. One of the biggest, Mount Takahi, produced enough CO2 and halogen gases at the end of the last ice age to have maybe accelerated the rate of change to modern conditions. And it's not stable. The West Antarctic ice sheet in places has a lot of water at the base, some of it resulting from melting of ice by subglacial volcanic activity. As it falls apart, then there could be accelerated volcanism in that region, in particular, the West Antarctic Rift Valley. So we look at these factors as influencing volcanism, magmatism on a longer term time scale than the period 1850 to the present time, the Industrial Revolution, that so concerns people at present.
It's interesting talking about Antarctica because I understand there are a lot of volcanoes buried under all that snow and ice. So the potential for those to not even a total ice melt, but with that ice partially melting, the weight coming off, doesn't that increase? You mentioned subglacial melting. I mean, as that ice starts to lighten and raise, doesn't that increase the volcanic activity underneath and accelerate the melting from the bottom?
Surely it does. If you decrease an ice sheet that's 1,000 feet thick on crust with volcanoes that have shallow magma chambers, I'm talking a mile or two deep or more, that decrease in load, even a few megapascals pressure is enough to make it easier for volcanic activity to occur, primarily by stimulating the exsolution, the coming out of solution of gases. That's a major driver of volcanic eruption through decreased load. But even going down deeper into the mantle, that decrease in load will allow a greater amount of partial melting to take place. So the pace of magmatism may increase.
Paul?
Yeah.
Yeah, so I think the other thing we should talk about with volcanoes that we haven't in the short term is they are very effective at actually cooling the climate over months to a few years, especially these large stratovolcanoes that places like, let's think about Mount Rainier in the continental US and a lot of the Alaskan volcanoes that put a large amount of sulfur aerosols into the atmosphere. And so there are volcanoes like Mount Tambora did this, and some of them have actually caused what was called the year without a summer, 1816, 1817, where it got really cold because so much of these sulfate aerosols ended up in the atmosphere that we didn't get as much sunlight coming through, but they wash out pretty quickly. But they can definitely mess with climate on a very human timescale. Mount Pinatubo did the same thing. So Rick, you can talk at much greater depth than I can about those.
Well, no, you speak of two scales of consideration here. One is the short, sharp, extremely violent volcanic eruptions like Pinatubo or Tambora or the like. And yes, there's a lot of sulfate that's put out. Pinatubo put out 20 megatons of sulfur dioxide into the stratosphere. And that did cool the Earth off for 2 or 3 years by about 1 degree Fahrenheit. And that may not sound like much, but that kicks us halfway back to the little ice age, really, if it's protracted. And the sensitivity of civilization to climate change can be underscored by an eruption that took place in Iceland about 1,000 years ago, the Elja fissure eruptions, 935 or so AD. which put out about 185 megatons of sulfur dioxide. Those eruptions were protracted. They lasted for perhaps as long as 9 years or so. And they had a global impact, most significantly in China, causing a sequence of summers that were characterized by drought and locust infestations and the like, and very cold winters. And this really brought a close to the later Tang civilization, the dynasty there in China. So sensitivity there to unstable climate conditions. I don't want to keep speaking too long about this, but I want to draw attention to a more significant role of volcanoes and their climate impact with regard to a much bigger class of eruptions we haven't seen taking place in human times, and that is the phenomenon of flood basalt eruptions. These are massive outpourings of lava from Earth's mantle that dwarf anything that we've seen historically. A spectacular example being eruptions that occurred over a period of 1 million years in Siberia, what's now Siberia, 250 million years ago. And you can imagine those alga eruptions, 2 of them occurring every year over a period of 1 million years, the amount of gas put into the Earth's atmosphere. Well, the 2 gases that are coming out, one is the sulfur dioxide, which cools the atmosphere, as you note, but there's a lot of carbon dioxide coming out as well. And that has the opposite counterbalance impact. That warms the climate. And nature can scrub sulfur dioxide out of the atmosphere pretty quickly, 2 or 3 years after a big eruption like Pinatubo, but not carbon dioxide. No, that persists. And so the net impact of those eruptions in Siberia 250 million years ago was to greatly warm Earth's climate, and to do so enough to raise sea surface temperatures over 100 degrees Fahrenheit, substantially higher than we have today, and so acidify the oceans that the marine food chains collapsed, and we had extinction of 95% of the species, whole biological families on the Earth. It just characterizes the end of one great geologic period and the launch pad for another. So, man, these are titanic, life-threatening events we haven't seen historically, thank gosh, and on timescales that dwarf what most people can easily perceive or grasp.
So those major events are obviously catastrophic, but I'm hearing even the shorter events. And you talk about an eruption that may get scrubbed in 3 to 4 years. But when we're looking at feeding 7, 8 billion people, 4 to 5 years of food system collapse is going to wipe out a massive portion of that. So that's kind of harking back to the idea that civilization is threatened more than individual humanity. Paul?
No, I think that's a really interesting point. So Tambora and the Year Without a Summer caused famine in parts of Europe and large parts of North America because people couldn't grow their crops, especially in the northeastern part of the United States. And so that's just 1 year. So you're right. And I think the other thing that's happening is as we get more people, we're getting closer and closer to the edge of the sustainable, I guess, of what Earth can sustain, right? And we are also very dependent now on synthetic fertilizer. Our soils are in large part degraded. We're dependent on fossil fuel energy to create this much food. And so I think there's less resilience in the system if something goes badly wrong. And I think you can see, the interdependence in the globe through, I realize it's a current event right now, but it's going to be an event for a long time, I think, is that the change in global trading patterns that are going on. And yet, that is critical to feeding folks, that food moves around the world. And so I think we've put ourselves as a society in a really kind of high risk position without a lot of resilience. So that, I try to imagine here where I live, let's say that we couldn't get fresh fruits and vegetables in the winter, or that the price became prohibitive to get, I don't know, your Hawaiian pineapples to Vermont, or lettuce from California to Vermont. Like, what would we do to live here? Well, we'd eat a lot of cabbage and carrots and potatoes and squash. And some of our farmers are getting pretty good now at growing overwinter spinach in hoop houses without heat. But our diet would change dramatically. And do we have enough land here to actually feed the people who live here? And I can say in our agricultural state, we might actually be able to do that. But then think about some of our mega cities, right? And if that food supply chain breaks, what happens to New York and LA and Chicago and those sorts of things? So again, I don't think of myself as a pessimist, but maybe a realist, that these climate perturbations, which are increasing in intensity and increasing in frequency, I think set us up for a disaster. And I'll just add one more thing to the Tambora piece that's kind of legend, and who knows if it's actually true, but that was the summer that Mary Shelley wrote Frankenstein. And I think that's a fun tie back to that. And she spent the summer actually having an affair right on the lake in Switzerland with Percy Shelley, and wrote Frankenstein because it was pouring rain and dark and cold and miserable, apparently was why that kind of book was created. So I think that's just an interesting tie to the sort of social science and literary piece that comes with this.
It is. Paul, talk about the geomorphology of Greenland.
Geomorphology of Greenland. Okay, Greenland is 80% ice covered. And actually, we know a lot about the geomorphology outside of the ice because we can see it. And we actually know a lot about the geomorphology under the ice because radar helps us see it. So there's a NASA program called Ice Bridge that flew tens of thousands of kilometers of lines back and forth across the ice sheet. And so we actually know that the center of Greenland is deeply depressed. Not that it's unhappy, just that it has this 2 mile thick ice sheet weighing it down, and it's actually below sea level. So if tomorrow Rick were to snap his fingers and melt all the ice in Greenland, it would actually be an archipelago with a connection to the ocean in the center, and essentially a big I don't know, a big sea, contained sea in the center. That would eventually disappear as the land rebounded over thousands of years because the weight of the ice was gone. There are giant canyons underneath the ice that are probably left over from when there was not an ice sheet there. There are impact craters from impacts of presumably asteroids. One of them is about 50 million years old in the northwest corner. So there's a fascinating geomorphology under the ice. There are lake basins filled with sediments that hopefully one day we'll figure out how to drill into and get that stuff back. But the bottom of the Greenland ice sheet preserves a history of when that ice was there and when that ice sheet was gone. And that's been my focus over the last 5 years, is trying to help interpret that from a very few samples we have from people who have drilled through that ice sheet. But outside the margins, I've spent 4 field seasons out there. It is one of the most amazing places in the world. It is rugged beyond anything I have experienced in my life. It is empty of people and what they do beyond anything I've experienced in my life. There's no road network, there's no island-wide energy network. There are scattered airports, really one city at Nuuk, and then a number of villages. But it's unlike, I say, anything most people have experienced in their lives.
Here it talks about mining Greenland, developing Greenland for geostrategic purposes, whatever. How is that going to impact climate and the rest of the world?
Oh, I don't think it's going to impact climate because I don't think it's actually going to happen. Um, Private industry has had more than a century to mine Greenland, and there are exactly 2 active mines in Greenland. One of them is quite an old mine that was used for a mineral called cryolite, which for decades was integral in producing aluminum and smelting aluminum. In fact, it was so important the U.S. sent hundreds of troops and garrisoned them there in World War II to make sure we had control of that mine. But it is a ridiculously hard place to work, having done field work up there and spent days on the ground, grounded when the helicopter couldn't fly, the airplane couldn't come pick us up. It was too windy for us to do any field work. I've had friends pinned down for the better part of a month in East Greenland. I find it really hard to imagine that we are going to be mining at an industrial scale there, just because the challenges are so great and the costs are so great. There have to be places in the world easier and cheaper to get the minerals that we need. So I'm not worried about that as a climate impact at all. I am far more worried about the global, and refusal is probably not the right word, global inaction on reducing carbon emissions affecting Greenland's climate than any activities that would go on the island itself.
So, and that's the ice melt, worried about the ice melting.
Oh, the ice is melting already. We have incredible data from a set of satellites called the GRACE satellites. They measure the gravity, and they are sensitive enough to see the snow come on Greenland in the winter and the snow melt in the summer and the ice sheet shrink. So since 2002, we have exceptionally good records of the shrinkage of the Greenland ice sheet, which is melting. And that meltwater goes into the global ocean, and it's just like leaving your tap on in the bathtub, the water level rises. And the global ocean right now is rising about 4.5 millimeters a year. That doesn't sound like much. I can just put my fingers apart like that. But that rate is increasing, and it adds up over time, right? And so if you all have a hurricane, and by 2100, the global sea level is 3 or 4 feet higher than today, that hurricane may just push the water into a place where it destroys the businesses, let's say Hilo, that otherwise would have survived without an extra 4 feet of water, or people's homes, or people's lives. So the impact of Greenland, I like to say Greenland wraps its arms around the whole world. People dramatically underestimate the threat of melting that ice sheet to everything we think about. Every coastal city in the world is going to be affected. And the only way to save that ice sheet is getting the carbon dioxide out of the atmosphere and not putting any more of it in there. It's simple. There's nothing difficult about that. Carbon dioxide in the atmosphere warms the Earth. As the Earth warms, just like you leave your freezer door open, the ice sheet's going to melt.
So it sounds simple. I mean, it is simple from a scientific point of view, but from a human point of view, how easy is? I mean, what's the role of science communication and climate change education, public communications? Rick, how do we educate the public and take action on this?
Well, yeah, I don't
Tough question,
really want to
huh?
get involved much with the political angle. You have to be to a certain extent sociological about it, though. I think a lot of people are well aware that there's a serious situation with the climate, and I venture if you went into the eastern part of Botswana and asked some of the indigenous people there if they've noticed change in climate and if they're concerned, you might actually find there's some awareness. We're bound together in a codependent global socio-political economic system, really, that makes it tough to take action without collective consensus. And so I think that it's really important for people that leadership is meant to serve leverage action on the part of that leadership. It's true, I think, for a lot of the great changes, the paradigm shifts in political action that have taken place historically, that it's the leaders follow the pressure exerted from below. So it's important for people to where they can exercise those avenues of making change collectively that are available. And individually, of course, we can make choices or decisions that are a compromise between what's practical and what's what we think should be done. That's correct. Buy, for example, an electric vehicle that you power with solar panels on the rooftop and so on and so forth. And that's a case by case sort of step that can be taken. There is, of course, a huge moral equation here. I think people who have kids who and concerned about their futures are going to take a longer view more readily than folks who don't. That isn't always the case, of course, necessarily. And I do think that that's where we begin to get into the question of civilizational stewardship. And again, I want to emphasize there are two pillars on which a civilization stands. One is consistent enough year to year climate conditions that you can grow crops to develop a surplus that will sustain civilization. But the other is stable sea level. And Paul has alluded to this, a change in the sea level. We need a stable sea level in order to enable trade to take place, in order to enable this consensus to take action to occur as a collective. And now stop and think about a 5-foot rise in sea level, Port of Los Angeles or New York. How easy would it be to pick up that port and move it inland a mile or two? Countless billions or trillions of dollars in terms of maintaining the physical basis for trade and global economy. So that's not a trivial long-term view, and it's one that tends to get lost in the arguments that currently dominate our conversation about climate in the media and in politics. But it's out there and it's not going away. And ultimately, I think we have to care. That's the bottom line. We just have to care.
So I'll take a different tact on that. I actually think as a climate community, we've made the mistake of pushing this as sort of an ethical and moral imperative, and we've not spent enough time communicating the practical side of this. And I wrote a short essay a couple weeks ago on the military paying attention to climate change because it was absolutely practical. And I reflect on that. I also reflect on the fact that the Clean Water and Clean Air Act were brought to us by Richard Nixon and the Republican Party. And most of my students just, their jaws drop because all they've known in their time is that the Republicans are supposedly anti-environment. And I have to say, that's not, that this is recent. This is not anything that goes back in time. So I think the way we have to do this is not by appealing to, you know, moral high ground and not by calling this a partisan issue, but by making sure that everybody knows this is a human issue across all political parties, across all nations. And Rick gets at that with the fact that civilization requires this collaboration and thinking toward the future. And I think he's also very right that it has to come from the people and the demand has to come from the people. But I think very much like our Earth, that the people on this Earth are going to at some point cross a tipping point. And that tipping point is going to be enough misery, enough damage, big enough storms, enough heat waves where the public is going to say, this is not acceptable. This is not okay. And then our leaders will follow from that. But I think my greatest emphasis in my science communication right now is that this is not partisan. This is not political. This is simply a matter of not only survival, but survival in a way where you can enjoy life and there's stability to it. And I think that's crucial. And that's a message that has not well come from scientists and the climate community in the past.
And that's our quality of survival. I want to thank you both for joining us today. Our time has really gone fast. So a lot of good information. Paul, I know you got a new book out when the ice is gone. Where can people go to learn more about that?
It's WW Norton 2024. You can get it from their website. You can get it from your library. You could get it from Amazon or your local bookseller.
Excellent. Excellent. Rick, where would you like to send people to learn more about your work?
Well, I do think that it's the series, the Oxford Encyclopedia of Agriculture and the Environment is a great reference. There's some compelling articles in there concerning climate change and what's going to happen in Africa and the human impact on the Holocene and the like. Otherwise, if folks are bound for Hawaii, take a look at Roadside Geology of Hawaii. It's accessible for everybody and give you good insight into the geomorphology and past as well as the current roadside attractions in the 50th state.
Well, thank you. And thank you to our listeners. We welcome your questions and feedback. You can learn more about the Climate Hour at climatehour.net. That's climatehour.net. This is the Climate Hour. I'm your host, Bob Grove.